Okay, so what about the next bits though? What about this thing called t-stat and this thing called p-value? What's that about? Well, that's all about testing the hypothesis that the true slope is 0 against the alternative that it's not 0. Now, the reason we care about this hypothesis is that if y and x are unrelated, let's say y and x are unrelated, what's the best fitting line? The least squares line in this case. Well, at this value of x, the mean should go through around about here. At this value of x, the mean should go through about here. At this value of x should go through about here. Join the dots. The best fitting line should be flat. If x and y are independent, the true slope should be 0. So often when we fit a linear regression line to data, we want to test the hypothesis that the true slope is 0 to test for evidence that we have a relationship between x and y. So we want to test for evidence against the claim that the true slope is 0. We know that the estimated slope minus the true slope over its standard error is standard normal. There's a sigma in there we need to replace with an s, which was estimated with n minus 2 degrees of freedom. So our test statistic then, which we get when we replace sigma with s, has a t n minus 2 distribution if our regression assumptions are satisfied. So if we're then going to go and test the hypothesis that the true slope is 0, if this guy here comes from a, let's say, n minus 2 distribution, then under the hypothesis that the true slope is 0, we can get rid of that, can't we? And we can just say, if beta 1 is equal to 0, then we're subtracting 0 on the top there. This statistic here comes from a tn minus 2 distribution if the true slope is 0. So now we got a statistic we can use to test the hypothesis that the true slope is 0. Basically what we're doing here, remember this guy on the bottom is the standard error. That's the standard error of the slope. So we're taking the slope estimate, dividing by its standard error, which tells us how many standard errors away from 0 we are. Let's go back to the output. So we have a slope estimate of 14.987 with a standard error of 1.339. If you divide the estimate by its standard error, you end up getting 11.192. So how far is our estimated slope away from 0? It's 11.2, about 11.2 standard errors away from 0. Is that unusually far? Do we have evidence against the claim that the true slope is 0? Do we have evidence of a relationship? Well, how often would you expect to get further than 11.2 standard errors away from 0? If the number of standard errors away from 0 you are has a tn minus 2 distribution. In this case, it's a t18 distribution. Well, I could work this out. I could go, what's t CDF? I could go, what's t CDF of 11.192, 18. I'll have to subtract that from 1 and double it. I end up getting about 1.5 times 10 to the minus 9. That's the last value in this table. Okay? So there's this p-value column of the table. The p-value column of the table is telling us what the p-value is for a test of the hypothesis that the true slope is 0 against the alternative that it's not 0.